Welcome back to eCoreAcademy, everyone. My name is Anita Raj, and I am a co-founder here along with my younger brother, AJ Raj. Today we have a new Algebra 2 lesson where we're going to be continuing the inverse variations topic. Today, specifically, we're going to be looking at graphs of inverse variations, and we call these graphs the reciprocal function family. Before I jump into the lesson, please make sure to like, subscribe, comment, hit the post notification bell, and share using our socials. So let me get right into an introduction as to what the reciprocal function family is. Graphs of inverse variations have two parts or branches. And if you look at these two parts, you'll see that these parts or branches are symmetric. Symmetric means if we reflect them about a line, both sides are mirror images of each other. And this you would see like on a graph if you actually graph this using the coordinate plane. And they are symmetric about the line y equals x or y equals negative x. Y equals x is just a regular line. It's a linear equation. In this case, the y-intercept is 0, and it has a slope of 1. Because if you think of it, y equals mx, in this case, the coefficient in front of x is 1. So it's just a regular line that's increasing if you consider it y equals x. But if you look at y equals negative x, which you'll sometimes see if the reciprocal function family is negative, it just goes the opposite way. It's just a decreasing slope. So the slope would be negative 1. And these inverse variations have two parts to them. One part will be below the line y equals x, and one part will be above the line y equals x. But if you reflect them, they look nearly identical to each other. And when I show you images of these graphs, you'll hopefully understand. Reciprocal functions are the parent function where f of x is equal to 1 over x, and where x cannot equal 0. So the parent function is 1 over x, and just like regular functions, you'll have different kinds of transformations, specifically translations, where we move f of x equals 1 over x horizontally or vertically, or sometimes we'll stretch it or compress it vertically, sometimes we'll reflect it over a line. So this is your basis, f of x equals 1 over x. That is your basis for inverse variations, but we'll be ending up manipulating this parent function to get different versions of inverse variations, and obviously x cannot equal 0. Whenever you have a fraction and you have a variable in the denominator, like in this case 1 over x, the denominator cannot be equal to 0. So if you had some constant such as 1 in the numerator and then you had 0 in the denominator, that just does not exist. It's not possible. You cannot have 1 over 0. You can have 0 over 1, which is equal to 0, but again, you cannot have 1 over 0, and you would get 1 over 0 if in this case x was equal to 0. So then if we're going to look into how do we graph these reciprocal function families, here are some tips. First, you want to identify the vertical and horizontal asymptotes. Remember, an asymptote is just a value that the function approaches infinitely, but it will never actually reach that function. So if you look at an xy table of the coordinates in that function, you will not see the value of the asymptote in the function table. Vertical asymptotes go up and down. That's x equals some constant. Horizontal asymptotes are horizontal. They go this way, right to left, and it's when y equals some constant. So I'll teach you later on in this lesson how to figure out where those asymptotes are. They'll be essential in figuring out what the graph of an inverse variation looks like. Next, you want to make a table of values, an xy table, after you figure out the asymptotes, because this will help you plot points and then connect those points. And make sure you include negative values as well, because including negative values will help make sure you get both sides of the inverse variation, both branches or both parts. We as students are typically more comfortable working with whole numbers, positive numbers, but in this case with inverse variations, you're going to have to include some negative values because you want to get both sides of the inverse variation, like both parts of it, both branches. With that being said, we're going to get into a key concept, and that's kind of an introduction to what translations are in the reciprocal function family. So again, like I said, the parent function is y equals 1 over x, where x cannot be equal to 0. With that being said, here are some ways to manipulate that parent function. So if we want to stretch the function, we're stretching it vertically. So we're pulling it up. We're stretching it out. Think of like a piece of candy or a piece of gum or a piece of taffy. If it looks like this and we're just pulling it up and down, we are stretching it vertically. And that's what we're doing here. And in order to stretch it, we would rethink of y equals 1 over x as y equals a over x. You see that these two forms look the exact same way, except a is in the numerator instead of 1. And a is going to be some constant. So if the absolute value of a is greater than 1, we're stretching it vertically, we're pulling it. That means that a can be equal to 4, -8, 10, any value we want, but it just has to be a constant. It doesn't matter if it's positive or negative. as long as it's greater than 1, the absolute value of it's greater than 1, the parent function will be stretched. The opposite is true if you have a value between 0 and 1. If the absolute value of a is between 0 and 1, that means we're going to be shrinking or compressing it vertically. So it's like we're making it wider, or you can think of it as making it a little bit fatter. You're just compressing the function vertically, and that happens when a is a fraction. So that would be like y equals 1/2 over x. That wouldn't be the proper way to write it, but if you had a as a fraction, that's when you would shrink or compress the graph. And then if a, ignoring the absolute value signs, if a is a negative number, meaning a is less than 1, you're just going to reflect it across the x-axis. And I hope that's kind of a reminder from when we did quadratics, because they're really similar in this way. Next, if we look at translations, this is if we're moving the graph up or down or left or right. When we're moving the graph, if you look at this new form, y equals 1 over x minus h plus k, where x cannot be equal to h, because if x is equal to h, let's say x is equal to 2 and then h is equal to 2, then you're going to get 1 over 0, and that's just not defined. So x cannot be equal to h. This h here determines how you're going to move this graph left or right, and this k that you add to the end is going to determine how you move the graph up or down. That's why it says horizontal by h and vertical by k. Therefore, if h is a positive number, for example, you're going to be moving to the right. If h is a negative number, you would end up getting x minus h, so that would end up being x plus h, and you would move to the left. It's a little bit tricky, but it's the same thing as vertex form. It's very similar to vertex form from when we did quadratics. And then the plus k is pretty simple. If you have a plus k or a positive k, you're moving the graph up. If you have a minus k, you're moving the graph down. So that's pretty much all there is. And to determine the vertical asymptote, you are actually going to end up setting x equal to h. And you might be thinking, you just told me not to set x equal to h. Well, that's because in our table of values, we're not going to get a situation where x is equal to h. But if you do set x equal to h, you will determine where the vertical asymptote is. And if you think about this, the vertical asymptote is an asymptote that the function approaches, but it will never be equal to the value at that asymptote, which makes sense because that value is never going to appear in our table of values. So you would set x equal to h to find the vertical asymptote, and then to find the horizontal asymptote, you just set y equal to k. And then if you combine all of these things that we learned together, you'll get y equals a, which is going to determine how we stretch, shrink, or reflect the graph over x minus h. Remember, h determines how we're going to move right or left, plus k, which determines how we're going to move up or down, and x cannot equal h. Okay, so let's get into some translations, and here's our first scenario. Our parent function is y equals 4 over x. You can see that this isn't typical because what we were looking at was y equals 1 over x. So in this case, a is equal to 4. And if the absolute value of a, in this case, the absolute value of 4 is 4, if that is greater than 1, then we're stretching the original function vertically. In this case, we're just told the parent is y equals 4 over x, so we don't need to worry about that. But just so you know, that's how y equals 4 over x is different from y equals 1 over x. Our new function that we're given is y equals 4 over x plus 4. So x plus 4 is in the denominator now, and we're trying to determine some properties about this function. So how is this function transformed? Well, you can think of 4 as h, but we have a plus sign here. Typically, we would have y equals 4 over x minus h. Here we have x plus h. That means that the 4 is actually negative because x minus 4 would be x plus 4. So if it's minus 4, we're going to be moving to the left, actually. So if you ever see a plus sign, that means you're moving to the left. If you see a minus sign, you're moving to the right. So that's why this graph is shifted left 4 units. If we're trying to determine the vertical asymptote, remember, that's where you set x equal to h. H in this case is negative 4, like we said. So x is equal to negative 4. That's where the vertical asymptote occurs. Because we don't have a k in this case, you can think of this as plus 0 because we have no k. Our horizontal asymptote is going to be y equals 0 because we don't have a k out here. We don't have a constant being added or subtracted to this whole thing right here. For our domain, think of it this way. When there's a asymptote in the way, there's going to be a discontinuity. And remember, we talked about discontinuities as being breaks in the graph. The graph doesn't have a value there. It's not defined there. Therefore, if there's going to be a break, that means the domain is not continuous. It just doesn't go from negative infinity to positive infinity without having any problems at all. In these cases, we do have a problem, and that's when x equals negative 4. X values are going to be your domain, so there's going to be an issue at negative 4. So that's why I wrote it this way. The graph is fine from negative infinity, and it keeps going, but then when it reaches x equals equals -4, there's a vertical asymptote right in the middle, splitting the graph, disrupting like its continuity. So that's why we put -4 union -4 to infinity. So this indicates that at that one value, -4, the function doesn't have a value. So that's why this is just the proper interval notation. So make sure you take note of this. And then if we look at the range, it's the same thing. We have a horizontal asymptote as y equals 0, and we write it the same way. The graph will continue perfectly fine up, down until you get to y equals 0, which is the x-axis, and that's where the graph breaks. And because it breaks there, it doesn't have a value there. So then after you pass y equals 0, you're perfectly fine. It's just at y equals 0, you have an issue, so that's how you would indicate it using this notation here. Here's another example. Y equals 4 over x. It's the same parent from the previous problem, but in this case, we get the translation y equals 4 over x plus 2. So what do we learn about this? So the plus 2 here is going to be k, and k tells us how this function is translated vertically. Because it's positive, we're moving up 2 units. As for the vertical asymptote, if we look at x, well, we don't have like an h attached to the x. We don't have an x minus h or x plus h. We can think of this as x plus 0. There's nothing there with the x like we had up here in these parentheses. Therefore, our vertical asymptote is going to be x equals 0. However, we do have a k added to the end, and our k is going to determine where our horizontal asymptote is. In this case, k is equal to 2, so y equals 2 is going to be our horizontal asymptote. As for the domain, we're just going to use our vertical asymptote, and we determine that there's a break at 0 because there's a vertical asymptote there, but otherwise, this function continues from negative infinity to positive infinity, just with that one break at 0. And the same thing for the range. We determine there's a horizontal asymptote at y equals 2. So this function continues from negative infinity to 2, where it reaches the horizontal asymptote, breaks, doesn't have a value there, and then it continues from 2 to infinity. So those are some translations. Here's our first problem where we're actually going to be graphing. In this case, you would just be given this inverse variation y equals -1 over x minus 7 plus 3. You just be given a coordinate plane. You have to graph everything, and you have to determine the domain, range, vertical asymptote, horizontal asymptote. Remember, the first thing I would do is determine where are the vertical and horizontal asymptotes. We can determine the vertical asymptote by looking at the denominator. This is technically x minus h. In this case, h is equal to 7. Because h is equal to 7, if we set x equal to h, that means x is equal to 7 is where the vertical asymptote is, and that's why I wrote x equals 7 here. To determine the horizontal asymptote, we have to look at the plus k. In this case, k is equal to 3. So our horizontal asymptote is y is equal to 3. With this information, you can create an xy table. And for this case, I said to include negative values before, but by finding the horizontal and vertical asymptote, you can determine kind of where the branches are going to be, because they're going to be on opposite sides of the asymptote. So what I did was I graphed the asymptotes. Here you have y equals 3, and here you have x equals 7. When you graph it, I would make like a dashed line or something to indicate that these are the asymptotes, because right here where my cursor is, these are the axes, and you don't want to confuse yourself, because by putting dashed lines you can indicate these are asymptotes, these are axes, there's the difference. Then what you want to do is you want to pick values that are close to these asymptotes, x values specifically, and create an xy table. Because I saw that the vertical asymptote is x equals 7, I picked 3 values to the left of it. So I picked x equals 4, x equals 5, and x equals 6, as you can see. Then if you look at x equals 7, that's where the asymptote is. The function doesn't have a value there. It just continues towards infinity, but never actually touches x equals 7. Then I looked at 3 values that come after x equals 7, x equals 8, x equals 9, x equals 10. I added those to my xy table. All I did was I took these x values and I plugged them back into the original equation, because if I do that, I can get the corresponding y coordinate, which is over here. And by doing that, with simple math, I found all of these corresponding y coordinates. I plotted them, and I just connected them. And as long as you know the general shape for an inverse variation, you can just trace the rest of the graph, and you should be fine. As for the domain and range, the domain, you look at your vertical asymptote, you can see that this function continues. If you look right to left, it continues. It doesn't have a break. It doesn't have a break until it reaches x equals 7. So that's why it's negative infinity to 7, union 7 to infinity. It only has an issue at x equals 7. If you look at the range up and down, if we go downwards, we don't have any issues. The function has a value until we reach x equals 3, where it breaks. There's no value at there's no corresponding x coordinate or value at y equals 3. So that's why there is a break at 3, and then it continues fine towards negative infinity. That's why we have negative infinity to 3, union 3 to infinity. that's how we would graph. Here's another example. It's pretty simple. We're just going to write an equation for the translation of y equals negative 1 over x. Oh, sorry. And something else I wanted to mention about the last problem. This says negative. And you shouldn't have an issue if you just plug your x values into this, but just know that this is like reflected because of that negative. You can think of that like a negative a. Okay, let's move on to the next problem. I just wanted to mention that to beware of the negatives, because here we have y equals negative 1 over x. Again, here we don't have to worry about it because we're told that this is kind of like the parent function in this situation, just like we were told y equals 4 over x was the parent function 2 slides ago. But we're being told that this is the parent function, and we're translating those 4 units left and 5 units up, and we're trying to write the equation. So if we do 4 units left, this is going right to left, like in the horizontal direction. So this would be h. This would be like a matter of determining what h is. So if you rewrite this, we're going to have the negative 1 over x. Then how do we determine our h? Well, if we're going 4 units left, we're going towards the negative side. So we're going minus 4. So if we have x minus h and we substitute negative 4 in for h, we end up getting x minus negative 4. And then the minuses become a plus, and you get x plus 4. And this indicates it's shifted left 4 units. And 5 units up, well, this is k. This is like our vertical translation. So we just add a plus 5 to the end of that, and means shifted up 5 units. And that's how you do a translation. Here's our last example, and I wanted to throw in a word problem just so you were exposed to this. So let's read it together and break it down. The rowing club is renting a 57-passenger bus for a day trip. The cost of the bus is $750. 5 passengers will be chaperones. If the students who attend share the bus cost equally, what function models the cost per student, C, with respect to the number of students N who attend? So let's stop right there and analyze this information. We're doing a 57-passenger bus. It can hold 57 people. The total cost of the bus is $750. So all these students have to be able to finance that $750 to be able to go on the bus. 5 passengers will be chaperones. And we're going to assume that these chaperones are not going to pay. Therefore, if only the students are going to be the ones paying, but you still got to accommodate for these 5 extra chaperones, we need to create a function that models how much each student will be paying. As in, how are these students going to be splitting the $750? So what I did was I determined we have 57 seats in the bus, and we have 5 non-paying chaperones. These 5 people, they're not paying for it, only the students are. So 57 minus 5 leaves 52 seats left for the students who will be paying that $750. So with that being said, we're going to be using this information and determining a function. So C is going to be equal to, well, that $750, that total amount, divided by the number of students who will be coming on the bus. 52 students is the maximum amount of kids we can have, but we could end up having 20 kids on the bus. We could end up having 45 kids on the bus. But no matter what that number is, the cost per student is equal to that total cost, $750, divided by the number of students, because each student who is on this bus is going to be paying for an equal chunk of that total $750. So that's how you determine C equals $750 over N. And this, as hopefully you can recognize, is similar to Y equals 1 over X, except in this case, it's still an inverse variation. So that's how we would create the function. Cost per student is just that total cost divided by the number of students, and that's going to give you cost per student. Then we're asked, what is the domain of the function? Well, we determined that only 52 students can attend max if we have those 5 chaperones also coming. There's only 52 seats left. Therefore, the domain can be anywhere from 1 to 52 students. The minimum, we're obviously going to have at least 1 kid on the bus. You could even argue that you could have no kids on the bus, but then there would be no point for this bus trip. So you can argue that there's going to be at least 1 kid. We can't have any negative kids or partial kids. So we're just going to go look towards the positive direction. And the maximum of kids we can have is 52, because we have those 5 chaperones as a set amount. We don't have the kids as a set amount. So the kids can be anywhere from 1 to 52. And that would be our domain. And again, like I said, integers only because it's people. You can't have half a person. It has to be an integer value. Then the last question is, how many students must ride the bus to make the cost per student no more than $20? So cost per student is our variable C right here. So if we substitute 20 in for C, that's where we get this inequality. We don't want kids paying any more than $20. So whatever we determine, this is our cost per student, and this is also our cost per student. And we want this value to be less than 20. We don't want it to be any more than 20. 20 is the greatest it can possibly be. So that's how we set up this inequality. And what we can do is we can plug this into a calculator, put 750 over x 750 over x into y1 and 20 into y2, you can find their point of intersection, and you'll get the points at 37.520. This means that in order for them to pay $20 exactly, as in no more than 20, 37.5 students must attend. Excuse me. And you can round this up to 38, so at least 38 students must attend. So that's it for the video. I hope you enjoyed. If you did, please make sure to like, subscribe, hit the post notification bell, drop a comment down below, and share using our socials. I hope you'll join me in the next Algebra 2 Inverse Variations video.